All right, so we're going to take a look at the graphs of secant and cosecant. And first of all, remember that secant of an angle, so we write that as SEC of theta, is defined to be r divided by x. And likewise, cosecant of an angle, if you recall, is r divided by y. Now, in both cases, we're dealing with fractions. And so to start this video off, we're going to start with an observation. And let's write that down. And it has to do with fractions and making fractions large. So to make a fraction large, we have two choices. So we have two choices. So the first is the obvious way. You can first make the numerator large. So 1, make the numerator large. Numerator, hold on. Okay, it turns out that there's a second choice that's going to be more important for us. And that other choice is to make the denominator small. Make the denominator of the fraction small. Let me give you an example of what I'm talking about. So let's look at, for example, 1 divided by 0.1. Well, that's equal to 10. Now if I leave the numerator alone, that is at 1, but I make the denominator small, so this is case 2 I'm about to show you. If you make that denominator small, or smaller, let's say, 0.01, you end up getting 100. So what happened? It wasn't that the numerator got large, it was that the denominator got small. Now we're going to want to denote this situation when we're dealing with secant and cosecant. And so the way we're going to write this, or the way we're going to think about it, we're going to use the following notation. We're going to use a little arrow, meaning, oh, as this situation happens, 1 divided by 0, and I'm going to write a little plus sign here. And that little plus sign means this, that, yeah, I'm approaching 0, but I'm doing so through positive values. So for example, 0.1 is small. 0.01 is really small, right? Getting closer to 0. Notice how those values are positive. Okay, as that happens, not only does the fraction get large, it gets large in a positive way. Okay, so this fraction we're going to write as you approach 1 divided by 0 from the right, this fraction goes to infinity. Okay, and that means that the fraction can be made as large as you'd like it. Now, another situation exists as well. Let me illustrate that with a few examples. You can have 1 divided by negative 0.1. Okay, and how is that different than what we did a moment ago? Well, it's a positive divided by a negative, and we know that's going to be a negative what? Well, negative what we had before, right? Negative 10. Now, if you keep playing the same game, and you then write 1 divided by negative 0.01, well, it's negative 100. So you see something similar is happening, right? The fraction's getting large, but it's going to negative infinity. So here's what we're going to write in that case, that we're heading towards 1 divided by 0. We never actually get to 1 divided by 0, but that's what we're headed towards. And I'm going to put a little negative right there telling you that we're approaching 0, yeah, but we're doing so through negative values. And what does that fraction go to? It goes to negative infinity. Okay? So the point is that you can make a fraction large by making the denominator small, and how the denominator goes to 0 matters. If it goes to 0 from the right, the fraction goes to infinity. If the denominator goes to 0 from the left, the fraction heads to negative infinity. Okay? So with that in mind, let's go ahead and tackle secant of theta, the graph of secant of theta. Okay. Okay, so the graph of secant of theta is going to be down here. I'm using this circle as a way to generate this graph. Now the first thing we want to do is acknowledge that secant of theta, right, as we mentioned in the previous on the previous video, that secant of theta is r divided by x. Okay, now you can choose any r you want. We're going to use r. We're going to choose r to be 1. That is, we're going to talk about r being 1, and that makes it what we call the unit circle. So let me draw in a radius of 1 right here. Okay, so this is 1, and of course this is the angle that we're considering, or this is the angle corresponding to this point right here that has coordinates x, y, for example. Okay, now first of all, there are, as far as the graph is concerned, there are a few values of theta that are easy to evaluate. Now we can get those points by acknowledging that we know a lot of the coordinates on the circle, right? So this point has coordinates what? Well, x is 1 and y is 0. And what are the coordinates of this point? Well, x is 0 and y is 1. And likewise over here, x is what? Well, x is going to be 0 and, whoops, not 0, x is going to be negative 1, right? And y is going to be 0. So x is negative 1 and y is 0. And then down here, x is now going to be 0 and y is going to be negative 1. So x is going to be 0, y is going to be negative 1. Okay, everything looks good. So now, if you think about secant, right, well, there are a few places where you know what x is just from these points, right? So I can see right here, for example, that is when the angle is 0, x is equal to 1, right? And r is equal to 1 as well. So that tells me right away that secant of the angle 0 is equal to 1 over 1, which is equal to 1. So I can put that on my graph, right? When the angle is 0, I get 1 for secant. So here we go. When theta is 0, I got 1 for secant of 0. Where else? How about over here? What's the angle? Well, the angle would be pi, right? So when the angle is pi, the x-coordinate is negative 1. So I know that secant of pi is going to be r, which is 1, and x is negative 1, so I get negative 1. So when the angle is pi, I get negative 1. Okay, and then finally, you can go, one more point, one more angle that's convenient. When the angle is 2 pi, that is when you go all the way around. Secant of 2 pi, and of course, x is 1 again, so it's 1 over 1, and you get 1. So secant of 2 pi is 1 again. Okay, now what we're going to do is we're going to make use of what we talked about on the previous page. Now remember, secant is always, it's always this, right? R over x. Now, what we're going to do is we're going to think about what happens as the angle goes from 0 to pi over 2. And I'm just going to draw that in right here just so we can get an idea of what we're talking about. The angle is going from 0 to pi over 2. Now, the angle's approaching pi over 2 from the left. And what I mean by that is that you're coming at pi over 2, but from angles that are smaller than pi over 2, right? So what we want to do is we want to link up that motion, if you will, with motion along the circle. Okay, so first of all, where's pi over 2 on the circle? It's right up here, okay? Now, if you're approaching from angles that are smaller than pi over 2, right, from the left, which way are you approaching pi over 2? From like that, or are you approaching like that? Well, clearly the first, right? Because if this is a point corresponding to the angle, right, this is a point on the terminal side of the angle, then that point is approaching pi over 2 in that direction, okay? So this little arrow and this little point moving in that direction corresponds to that arrow on this graph. That is here, this little arrow is telling me that theta is approaching pi over 2, but from the left, okay? And that's corresponding to this, right? Approaching pi over 2, but from values of the angle that are smaller than pi over 2. Okay, so why am I bringing that up? Because what does that imply about r over x? Well, let's see. As the angle approaches pi over 2 from the left, okay, r over x is approaching what? Well, r is 1, so that's staying 1. But x is approaching what? Well, the x-coordinate is approaching the value 0, right? Because that's what the x-coordinate is here. So x is approaching 0. Now, is x approaching 0 from the right or from the left? And you see how this point is in quadrant 1? The x-coordinate is positive in quadrant 1, right? And that's why x is approaching 0 from the right. And from what we talked about on the previous page, that means this quotient right here is approaching infinity. So, back to this graph over here. You're approaching pi over 2 from the left, and that means r over x, which is secant, is approaching infinity. And that's why the graph is looking like this. It's getting larger and larger and larger. As it gets closer to pi over 2, it's getting infinitely large, okay? So first of all, that means that we have what's called a vertical asymptote. So let's write that here, a vertical asymptote. And let's go ahead and graph that in now. See what a vertical asymptote looks like. Okay, so there we go. The vertical asymptote's at pi over 2, and we draw it with a dotted line. And the graph, right, it was at 1, but as we approach pi over 2 from the left, it's getting larger and larger. And we usually put an arrow like that telling the reader, hey, it's going to infinity as you approach pi over 2 from the left. Now let's do the opposite. Let's approach pi over 2 again, but now from the right. Okay? Now remember what that means. That means you're letting the angle get closer to pi over 2, but from values of the angle that are larger than pi over 2. So let's connect that with this graph over here. Well, pi over 2 is right here. Now where are angles that are a little bit larger than pi over 2? They'd be over here, right? So if I draw a point like this and I draw an arrow like that, that's telling you that the angle is approaching pi over 2, not from the left, but from the right, okay? So the point's moving in like this. And if we analyze it the way we did for pi over 2 from the left, let's write that down, as theta approaches pi over 2, but now we're approaching from the right, well, r over x approaches what? Well, r is approaching 1 again, and x is approaching 0, but which way is x approaching 0 from? Well, because we're in this quadrant right here, all the x-coordinates are what? Negative. So the x, it's negative, and it's getting smaller and smaller. X is getting closer to 0, but all the x's are negative. So it's approaching 0 from the left, and that's why this whole quantity is approaching negative infinity. Also, that's really interesting. As you approach pi over 2 from the left, it goes to infinity, but as you approach pi over 2 from the right, it's approaching what? Negative infinity. So that's why the graph is going to look like this. So let's draw that in now. So that's what the graph looks like coming to as theta, as the angle approaches pi over 2, but from the right. And so we put a little arrow indicating this. So the graph is actually going to negative infinity from that direction. And now looking at this, there's one more point to consider, one more angle that's really interesting, and that would be 3 pi over 2. So here's what we're going to do. We're going to approach 3 pi over 2 first from the left. Okay? Now as you come at it from the left, coming back to this graph, where's 3 pi over 2? It's right here. Now if you're approaching from the left, that means values of an angle that are a little bit smaller than 3 pi over 2, right? So you're coming in, or we're coming in like this. So this is, right here, theta is approaching 3 pi over 2, but from the left. So writing that up here, just like before, as the angle approaches 3 pi over 2, but from the left, well, r over x is approaching, well, let's see, r is again approaching 1, or r is always 1. And what's x doing? Well, x is approaching 0, right? X is approaching 0 here. Now, are the values of x positive or negative? Once again, they're negative because we're still in quadrant 3. So x is approaching 0 from the left, and once again, we're approaching negative infinity. What that means is, as you approach 3 pi over 2, from the left, we're expecting the graph to nosedive like this. Okay? So we're going to have another vertical asymptote, and the graph is going to look like that. So let's draw that in now. Okay, so as the angle approaches 3 pi over 2 from the left, the graph is dropping. It's going to negative infinity, right? So we draw it down. It's going down to negative infinity like so. Okay, now what about as you approach 3 pi over 2 from the right? So once again, you come to your graph. 3 pi over 2 is right here. But now you're approaching from angles that are a little larger than 3 pi over 2, right? So you're coming in like this. The angle's approaching 3 pi over 2, we say from the right. And then finally, if we analyze that similarly here, as theta approaches 3 pi over 2 from the right, well, what is r over x doing? R over x is going to 1 over, what's x doing? It's going to 0 once again, but now you're in quadrant 4. And in quadrant 4, the x is positive. So x is approaching 0 from the right, and that's why the quotient is approaching infinity once again. So as you come in like this, right, from the right, we know you go through this point, but now you go to infinity, so it goes like that. Okay? So drawing that part of the graph in gives us a graph that looks something like this. Now, of course, we want to make sure that we're clear that the graph is getting larger and larger as the angle approaches 3 pi over 2 from the right. Now, do you see where the vertical asymptotes are? Pi over 2, 3 pi over 2. Next one's going to be at 5 pi over 2. There's also going to be a vertical asymptote over here at negative pi over 2, right? So the graph, it looks like these series of up and down cups, right? So up, and then down, and then up, and so on. Now, if you were to graph in cosine, you would find that cosine, the graph would look something like this. So there's a close connection between the graph of cosine and the graph of secant. That is, they're reciprocals of each other. Okay, so now that we know what the graph of secant looks like, or rather, if we were to graph in the graphs of secant and cosine are reciprocals of each other. So now if we were to graph cosecant, it follows a very similar pattern. And the reason is because, remember, cosecant is cosecant is not r over x, cosecant is r over y. So let's take a quick look at that one. So cosecant is r over y. Okay, so we're going to handle this very similarly, right? Now, cosecant is r over y. Now remember, you can start off by getting a few free points on your graph. And the reason is because, well, if you take the unit circle, that is a circle once again with radius 1, look for when y is 1. Well, when does that occur? That occurs at pi over 2, right? Y is 1. So at pi over 2, I get the value of 1. And when y is negative 1, well, y is negative 1 when the angle is 3 pi over 2. So I'm down here. Okay, now you can play the same game, and just to get you started, what do you think is going to happen as you approach 0? So as the angle goes from, you approach 0, but from the right. So what we're talking about on the graph is coming in like this. Now, that means you're coming at, here's the angle of 0, but you're approaching it from angles that are a little bit larger than 0. That would put you in this quadrant, right? So if you draw this, you're saying that the angle that you're approaching 0, but from the right. And you can write that out, right? As the angle approaches 0 from the right, what happens? Well, r over y, well, that's approaching 1. And what's y doing? Y is approaching 0. Now let me ask you, is y approaching 0 from the positive or negative values? Well, you're in quadrant 1, and the y's are all positive up here. So you're approaching 0 from positive values, right? Values a little bit greater than 0, and that means the fraction is going to infinity. So once again, you're going to have a vertical asymptote. And the vertical asymptote now occurs when the angle is 0. So we're going to draw that in along with the behavior of cosecant. And now I can see that as I approach 0 from the right, the graph is once again going to infinity. I have a vertical asymptote there. Now what do you think is going to happen as the angle approaches pi, but from the left? Well, here's the angle pi, and you're approaching from the left, right? That is angles that are a little smaller than pi. So now, in this right here, the angle's approaching pi, but from the left, okay? And as the angle approaches pi from the left, r over y is going to, once again, 1 over 0. Okay, but what's y doing? Approaching 0, but once again, from positive values, right? Because the y-coordinate is always positive up here. So y approaches 0 from the right, we say, our value is a little larger than 0, and so the fraction once again is approaching infinity. So as you approach pi, the graph is going to look like that. Now you might guess that in this next interval between pi and 2 pi, if this is an up cup right here, then this might be a down cup, and you'd be right. So I'm going to go ahead and graph in the rest of cosecant, and you should verify that indeed you get this down cup as you approach pi from the right and as you approach 2 pi from the left. Okay, let's see what the graph looks like. Okay, and once again we draw arrows indicating going towards negative infinity this direction and negative infinity that direction, positive infinity in that direction. And once again, there's a close connection between, in this case, cosecant and its reciprocal, which is sine. And if you draw in dotted the graph of sine, of course, it looks like this. And so everywhere sine is 0, the cosecant has a vertical asymptote. Okay, and that's not a coincidence. Those two functions are reciprocals of each other. Okay, so that's how we graph secant and cosecant.